let's begin. Today's activity will be on implementing these Python sparse solvers to solve the heat equation in the unit square. So we got del squared U equals 0 with Dirichlet conditions everywhere on the boundary. U equals 0 except for a small strip on the left wall where U is equal to 1. We will solve this on a finite volume grid because that's the grid that you will be using later through the end of the semester. And the standard finite volume discretization, central in space at for cell-centered quantities results in this discretization for U. U here is not the velocity field or the staggered quantity. This is a cell-centered quantity, just like the pressure. I just called it U, okay, just to designate that this is like a diffusion process like heat. Okay, so this would be the standard arrangement that you're looking at. And note that this is the discretization, and then we split the discretization so that we have coefficient times unknown plus coefficient times unknown, etc. So this is the equation at point uij. Okay, so equation at point uij relates the information at that point to the neighboring points. And note that the coefficient of uij for all interior points is simply the sum of all negative times the sum of all the other coefficients. So minus 1 over delta squared, minus 1 over delta squared, minus 1 over delta y squared, minus 1 over delta y squared. And if you recall, for simplicity, we use the a map notation, east, west, north, and south, and P for the point in question. And in that case, we simply convert this equation to A west U west plus A east U east plus AP U P plus A north U north plus A south U south. This is the equation at point P. Okay, and A west, A east, A north, and south are given by 1 over delta x squared and 1 over delta y squared respectively, and AP is negative the sum of all of those coefficients. Now this is valid at all interior points, but at the boundaries we need another treatment. So I'll give an example for the left boundary. So suppose that you have a Dirichlet boundary condition on the left given by U left, and you will have this kind of arrangement. There's no boundary point beyond that boundary. So we only have interior points, point P, east and north and south. But there's still a problem in trying to figure out what we will have to do for U west. Right, because it's undefined. Now, clearly, there's no west coefficient connecting to US because there's no U west, but we're going to have a fictitious, we need to somehow feel the effect of the boundary condition, U left. So we're going to create a ghost cell temporarily called U west that we're going to eliminate in a second. And we're going to say that the average between U west and UP, so U west plus UP over 2, is equal to the boundary value. So you see this equation, U west plus UP over 2 equal U left. That allows us to eliminate U west and express it in terms of UP and the boundary value, which is a constant in this case. So if you take U west and plug it back into our standard equation up there, A wall U wall, A west U west plus A east U east, etc., then you can eliminate U west entirely. And then you move things that you know to the right-hand side, which is A west times 2 times U left. So you get minus 2A west U left on the right-hand side, like over here. And then you will need to also change the coefficient of UP. And simply by decreasing it by a fixed value of A west, which is 1 over delta x squared. Okay, so this would apply at all of those Dirichlet boundaries. Okay, so think of it as having an equation at each one of those boundaries, and you're simply adjusting the right-hand side of those equations, so that would feed into the right-hand side of the system of equations, and you're adjusting the coefficients of these unknowns. Okay, so let's go ahead and grab our Python notebooks and get started programming this. I will zoom in. All right, so we will need to import some boilerplate over here, and we will start with NumPy, import NumPy as NP. And we will need to import some stuff from SciPy, import scipy.sparse.lin algebra. So that is going to give us spsolve conjugate gradient, and import matplotlib.pyplot as plt, import time to time our solutions, and import the algebraic multigrid, import pyamg, and then matplotlib inline, and the magic config inline backend dot figure format equal SVG. So we have nice looking figures. All right, let's start by defining our domain, and x equal and y equal 32 grid points. L is Lx equal Ly equal L equal 1. So that's our grid resolution, domain size. And then dx, because this is finite volume grid, so I'll create dx before I create the lin space. And dx is simply Lx over nx, and dy is Ly over ny. And we can now create a lin space for x. Remember, these are cell-centered quantities, so x is going to start from dx over 2 and end at Lx minus dx over 2. So we'll have mp.lin space dx over 2 all the way to Lx minus dx over 2 and nx points. And then y is equal to mp.lin space dy over 2 all the way to Ly minus dy over 2 with ny cells. Now we can declare our right-hand side. Okay, so the right-hand side is going to be a bunch of zeros, mp.zeros, and I'm going, although the right-hand side eventually is going to be a column vector of size nx times ny, I like to create it as an array that resembles the grid, so I can reason logically about what goes in the right-hand side at what point, especially near the boundaries. So we will create it as a two-dimensional array, and then we will flatten it, okay, turn it into a one-dimensional, just a one-dimensional column vector. Okay. So now at the left wall, we have u left was equal to 1, let's say, and then the right-hand side, at some portion of the left wall, if you remember the slides, at some portion of the left wall, we want it to be heated or be equal to 1. So we'll say, right-hand side from 4 to ny minus 4, and for at x equals 0, so that's equal to 1.0, so that should be equal to whatever value we obtained here, which is minus a west times 2 times u left. So that will be minus 2.0 times what is a west is 1 over delta x times u left. Agreed? And then we will flatten this. Now flatten the RHS array. We say RHS equal RHS dot flat dot reshape into a column vector of size nx times ny. And that will do the trick. Reshape. Okay, so now you can see, if you want plt dot matcho RHS, you can see that the right hand side has a value over here, some value over here, and everywhere else it's going to be 0. But this right hand side here is simply a one-dimensional flattened array. All right, so now it's time to build the coefficient matrix. And if you remember a while ago, or in the last lecture and a long time ago, I described that the way I like to build the coefficient matrix is by creating arrays for east, west, north, and south, and p coefficients that look like the grid. And then I can reason carefully about what the east and west coefficients and north, etc., need to be at each grid point, especially at the boundaries, and then flatten those and put them on the corresponding diagonal in the coefficient matrix. So we'll start with a east is 1.0 over d is 1 over delta x squared times mp dot 1s of size ny and x. So that gives us a two-dimensional array. A east, a west is the same thing, and then a north should be dy over here, and then a south should be also dy. Okay, but all of those are of size ny and x. And finally, the AP coefficient matrix is minus a east plus a west plus a north plus a south. So that will give you the correct coefficients for AP. All right, so now we set the boundary conditions, okay? Set the BCs. Okay, so let me make this go up a little bit here. Okay, so left wall coefficients. All right, so at the left wall, if you remember our equation, we don't have any A west over here because there's no connection to an A west variable, so it's always, all the A west are 0. everything was moved to the right-hand side or absorbed into UP. So we don't have a UWest variable. So there's no UWest variable, and therefore AWest for all y values at x equals 0 is equal to 0.0. However, we also need to adjust the coefficient for UP. We already have AP equal minus the sum of all of the other coefficients, right, which is minus 1 over delta x squared, etc. And then we need to decrease it by one more A west, which is 1 over delta x squared. So we do AP at the left wall, and minus equal 1 over dx over dx. Okay, so that should set us for the left wall. Now right wall coefficients, same thing for the right wall. At the right wall, we do not have any east coefficients. So A east at the right, for all y at the right wall, so x index minus 1 is 0. And same thing for AP. So for AP at the right wall, we have to decrease by 1 over delta x squared. Okay, because of the same reason that we, for the same reason that we had on the left wall boundary, because this is valid also at any Dirichlet condition, Dirichlet boundary really, except that at the right wall we don't have, u left is 0, and so it's not going to be accounted for in the right hand side. Now same thing for the other coefficients. So we go top wall, so that would be A north. For the top wall, that's negative 1 in the y. For all x, that's equal to 0.0, and AP also at the top wall is we're going to have to decrease it by 1 over delta y squared, 1 over dy over dy. If you're in doubt, write the equation at the top wall and see what happens to that equation. And then finally, bottom wall, we have A south. At the bottom wall, we have y equals 0 for all x values is 0, and AP at the bottom wall, y equals 0 for all x values, also minus 1 over dy squared. Okay? Okay. So now we are ready to reshape the arrays. And if you're confused about this, we can talk about it in a meeting or in the help sessions. But follow this strategy; it works all the time. I'm going to declare the total number of grid points as nx times ny, so that's the total number of equations. Obviously, our main diagonal is simply AP, and we're going to reshape that into a vector of size nx times ny, so that's n. Total number of grid points, main diagonal. Now the east diagonal is going to be contain all the east coefficients, reshape also of size n, reshape of size n. However, it should be of size n minus 1 really. So we have to get rid of one entry in the east diagonal, and that entry is going to be the last one, because there is no because the last point in your grid, the last point on your grid doesn't have any more east variables to connect to. So we knock out that entry. Same thing with d west is a west dot reshape of size n. It should be n minus 1. So we're going to get rid of one element. Now the first element in the grid doesn't have a variable to the west. So we get rid of that element, and that's going to be 1 all the way to the end. Now d north, and we will do, let's do d north. Okay, let's do d north, and that's going to be a north reshape again, but we need to get rid now of nx elements, because the north diagonal is nx away from the main diagonal. Now, which nx elements do we get rid of? Think about it. All the top row of entries doesn't have any connection to any north variables. There's no north variables anymore. So we get rid of nx entries at the last, for the last set of points. And same thing for the south is a south dot reshape of size n. And we will get rid now. There's the first nx points do not have south variables, so we get rid of the first nx points of that, and now we have all our diagonals created as arrays. And finally we can create the sparse matrix. We say a sparse is equal to sci pi dot sparse dot diags. And now if you look at diags, it needs the diagonals and then the offsets. So the diagonals are going to be put in as a list, any order you want. I like D0, D east, D west, D north, D south. And the offsets are the offsets of those diagonals, also a list. Main diagonal offset 0, east diagonal offset 1, west diagonal -1, north diagonal offset nx, and south diagonal offset minus nx. Now, for this, I always like to use a compressed row storage format. So this would be format equals CSR. All right, and that should build our sparse matrix. Now, can you check if it makes sense? Maybe you can at least visualize how it looks like. If you print a sparse, what it will give you is simply the connectivity matrix. In other words, only the non-zero entries and the values at those non-zero entries. So this first column here contains the indices of the non-zero elements, and the second column contains, so this would be the index in the matrix, and this would contain the value. So that's what a sparse contains. Now you can, if you want to show it, you need to convert it to a dense array. And to convert that, you use an API called toArray. So you could do plt.matchShow, so show the matrix, a sparse dot toArray. And you can now visualize the coefficient matrix. It looks pretty, it's all zeros everywhere except for these diagonals, but it doesn't show much. So if you go to 8 grid points, for example, and try to visualize it, you'll see the structure of the matrix. It's actually more involved than you would imagine. Okay, so let's go back to 32 points, and now we are ready to actually do a solution. All right, we will start with spsolve and start with spsolve. And I need a timer, so I'm going to do tick time.time. Not that it's going to matter for this problem, but it will matter for your homework assignment. I'm going to do solution is equal scipy dot sparse dot len algebra. So we already have spsolve. Let's see, scipy dot sparse dot len algebra dot spsolve. Okay, and we give it, so what do we give spsolve? You give it coefficient matrix and right hand side. Now sparse solver is an exact solver, so it doesn't need it take a tolerance. So we do a sparse and then right hand side. Now solution is going to be a, so talk equal time.time. Now sol is going to be a one-dimensional array. We need to reshape it. So sol spsolve is equal sol.reshape. Now we're going to reshape it to look like the grid ny and x, so two-dimensional array. And then plt.contourf x, y, sol spsolve. And we need, let's do 30 levels, and the color map is Inferno. And let's do p.x label x. Please put labels on all your plots. I don't do it because I don't have time in class, but you should have a good practice to do this. Title, solution with spsolve, okay, and then plt.color bar. And let's see. Oh, look at that. Very beautiful. Now there's an exact solution because spsolve is a direct solver. We got heating here for the, this strip, and everywhere else is 0. Okay, so now let's do the conjugate gradient solver. Same thing here, except I'm going to call CG in this case. Now for CG, you give it A and B, but you can also give it a tolerance. Okay, so we're going to do tol equal 1 e to the minus 6. Okay, and then sol conjugate gradient is, and then sol conjugate gradient and sol with CG. Let's see. Okay, so it threw an error over here. Sol CG is sol. Oh, yeah. So the conjugate gradient solver returns two parameters. Okay, returns the solution and some info. So we need to store this in like info, and now we have a solution. All right, great. This looks good. Now, comparing visually, okay, they look the same, but how can you tell? We simply take the difference. We say error in CG is equal sol spsolve minus sol conjugate gradient. I don't need to normalize here. Everything is between 0 and 1. I'm not going to normalize. And then I do an L2 norm. L2 norm for CG is mp.linalgebra.norm for error CG, and then print L2 error in CG is equal L2 CG. Now, what do we expect this to be? I expect it to be on the order of the tolerance that I specified, so 10 to the minus 6. So if we run this, we get 1.5 10 to the minus 5. That's pretty close. If we tighten the tolerance, 10 to the minus 12, same thing should happen. Now, L2 in conjugate gradient is 10 to the minus 12, as expected. Okay, so now we're ready to proceed to pi AMG. So again, I'm going to copy this and paste it here. All right, now pi AMG is a little different in the way you call the solution. So first you have to create a solver object. So I'm going to call this AMG solver is pi AMG. And like I said in the slides, we're going to use a Runge-Steuben solver, Runge-Steuben solver, pi AMG dot Runge-Steuben solver. However, you need to give it the sparse matrix, okay? Because this object is going to look at the matrix, and once you create it, it's going to create the algebraic multigrid, agglomerate the coefficients together, and get it ready for the solution. And then you solve it with a second step by calling AMG solver dot solve. And when you call solve, that's where you give it the right-hand side. And so if you, for some reason it's not giving me the API here. If you give it the right-hand side and a tolerance of 1e, let's say, to the minus 5, or 1e to the minus 6, and then cycle, like we said, I'm going to specify a v cycle over here, and then sol AMG is going to be sol.reshape, AMG, and AMG. If we run it, ta-da, we get a visually pleasing solution like the other one, consistent at least. Let's do the error in the AMG. Again, the SP solve is exact, so we can hold it as the truth. And AMG, L2, AMG, L2 in AMG, L2 in AMG. It should be the same, about 10 to the minus 5. If we change the tolerance here, it should decrease as well, 10 to the minus 9, consistent with almost pretty close to our target tolerance, okay? And that's how you would do it, all right? That's how I would do it. You can start playing around with boundary conditions here. So you should challenge yourself to say, okay, what happens if I put a Dirichlet boundary condition on the right-hand side over here on the right wall, or a Newman condition on the right wall? So for Newman conditions, remember, we did this with the finite difference case, where you have to do a derivative and approximate it, eliminate the ghost point, and see what happens to your coefficient matrix. Okay, so that should do it for today. Thank you for your attention, and I will see you next week.